As somebody who directs an exercise science lab, I can tell you there's been a huge growth and interest in VO2max testing over the last few years. Now, many of the people coming into my lab with interest in VO2max testing tell me that they've heard it's the best predictor of longevity, that they should get it assessed in the lab because it's the most accurate way to do it. And that's why they're showing up at our door. So in this video, I'm going to talk about VO2max, its links with longevity and health, and more importantly, do you need to actually get your VO2max assessed in a lab? Is that necessary for most people? Now, the first thing we need to get out of the way is define what do we mean by VO2max. VO2max is the volume of oxygen consumed during maximal cardiorespiratory or aerobic exercise. The way that it's usually assessed in a laboratory is to have somebody do a progressively increasing intensity type test, whether it's on a bike, a treadmill, some other piece of exercise equipment, start off at a relatively low intensity, and then over the course of maybe around 15 minutes, work them up to an effort that is sort of a maximal cardiorespiratory sort of an intensity that they can maybe sustain for a few minutes. They quit whenever they want to be done. And throughout that test, we're measuring oxygen consumption with a metabolic cart. Usually there's a mask on somebody's face, and we get a value from that test, a maximal oxygen consumption value. The typical units of measure that we're talking about is milliliters of oxygen per kilogram of body mass per minute. So when you Google, what is a good VO2max value, that's typically the unit of expression that you're going to get. It's a relative unit to kind of make sure that we're being fair when we compare people of different body sizes, because somebody who's 250 pounds is going to consume more oxygen than somebody who's 120 at a given exercise intensity because of just grossly different body sizes. So that relative VO2max is kind of the standard in terms of when we make comparisons across people of different sizes. Now, the next thing we need to address is how good is VO2max at predicting longevity? We're going to use one example study. There's a lot of literature on this, but this is, I think, a good study to kind of think through the power of VO2max as a predictor of health. And then also think through the potential value or lack of value for actually assessing VO2max in a laboratory when it comes to trying to evaluate health risk. So this study had almost 48,000 men who did a treadmill test to assess their fitness. And there's actually two groups. There was a group that was assessed sort of in the 1970s and 80s, primarily, and then a group that was sort of assessed in the 90s and 2000s. They wanted to see here, was there any difference between those time spans with regard to how good VO2max is at predicting death and mortality, with the idea that, well, maybe medical treatment has gotten so much better in the last few decades that VO2max maybe isn't as good of a predictor as it used to be because we're just better at managing chronic health conditions and risk factors for things like cardiovascular disease. But what you see in this graph is on the horizontal axis, we have fitness levels. Now, it's expressed in a little bit of a different unit of measure. It's in metabolic equivalents, or METs. To convert that to the typical VO2max numbers that we see, we need to multiply times 3.5. So if we take the lower end, 5 METs, multiply that times 3.5, we get 17.5. So that's the low end of fitness in this study. And then the high end, 15 METs, we're looking at 52.5, kind of on that upper end. So anywhere from roughly 17-ish to about 52 is the range of what we would think of as VO2max in this particular study. On the vertical axis, we have sort of overall mortality risk. Higher number means more risk. And what you can see here is that when you look at the people with the highest cardiorespiratory fitness or VO2 max levels, they have about a third of the risk of death as compared to people with the lowest VO2 max or cardiorespiratory fitness levels. So yeah, it is a quite strong predictor of longevity and early death when you compare people with really low levels of cardiorespiratory fitness to people with high levels of cardiorespiratory fitness. And this has been shown in many studies. So I'm not just cherry picking this particular study. It's shown across the board in both men and women. So although this example looks at men, you also see a similar pattern among women as well. So the next thing we're going to take a look at here is a study from 1980. And this is looking at the relationship between running velocity and volume of oxygen consumed during running. And what you see here, and it's plotting results from the study that was done along with a couple of other studies before it, you see a nice tight positive relationship between running velocity and oxygen consumed. So that begs the question, if you know how fast somebody is running or how hard they're cycling in terms of power output, or if you can somehow calculate workload, do you really actually need to measure their oxygen consumption directly? If there's a very strong relationship between workload and oxygen consumption, we may not really actually need to measure oxygen consumption directly. We can rely on workload, whether it be speed with running, power output with cycling, to get a good estimate of oxygen consumption without having to actually hook somebody up to a metabolic cart in a lab and have them pay $100 to $200. With the known tight relationship between speed, workload, and oxygen consumption, exercise scientists, even decades ago, were able to come up with field tests that can be done without expensive equipment to try and estimate oxygen consumption. Again, if you know how fast somebody's running or what their power output is when they're cycling, if we know that it's going to be tightly related to oxygen use, as long as you can accurately measure running speed or power output on a cycle ergometer, you can then accurately estimate oxygen consumption under most conditions. The tight relationship between workload or running speed and oxygen consumption is the basis for a lot of field tests that we have that people can go out and do on their own with limited equipment, with relatively little expense, and be able to quantify or estimate their cardiorespiratory fitness or their VO2 max without having to go into a lab to actually have it directly assessed. Now, what we're going to talk about is what are some of those tests and how good are they? And do they have any impact on the prediction when it comes to longevity and cardiorespiratory fitness? Meaning, if I use a field test to estimate my VO2 max, is that going to cause major problems when we think about health risk and VO2 max's ability to predict whether or not you're going to have, early mortality? Now, if we think about the example of a running field test, how long should the test be? How much time or how much distance? Well, one way we can kind of think about that is to ask the question, how long could an athlete sustain exercise at their VO2 max? So if you brought them up to the speed, running speed, for example, equivalent to their VO2 max, how long could they sustain that? The answer to that question might tell us how long a field test should be to estimate VO2 max. So here's an example study that looked at highly trained runners who had fairly high VO2 max values in the high 60s. And what you see here in this table is that on average, they were able to exercise for approximately 6 minutes at a velocity that elicited their VO2 max. Now, there's a range there from a few minutes to more than 10, but on average, we're looking at about 6 minutes for the time that these runners could sustain exercising at an intensity that equated to their VO2 max. So when we look at the duration of many of the most popular field tests to estimate VO2 max, it's no surprise that they're going to kind of fall in that sort of time frame, anywhere from maybe 6 minutes upwards of 12 minutes when we think about maximal effort field tests to estimate VO2 max. Now, in 1968, a physician named Kenneth Cooper validated one of these types of tests that is still broadly thought of as one of the most popular ways or common ways of estimating VO2 max in the field. It's the 12-minute run test. So basically what it involves is running as far as you can over the course of 12 minutes. And the distance that you run is related to your VO2 max. So if we actually measure your VO2 max in the lab and then have you go out and run 12 minutes as far as you can, if we have a group of people do that, there's going to be a fairly tight relationship between those two values. As you can see here from the original 1968 paper, there's a pretty strong correlation between the distance covered during the 12-minute run test and VO2 max values actually measured in the lab. Right, so running for 12 minutes maximally, that's very highly aerobic type activity. And again, it kind of falls in that maybe sort of few minutes to upwards of 12-minute time range that I talked about when we think about how long can people sort of sustain a running velocity that elicits sort of a maximal oxygen consumption. So we see that the Cooper test seems to be pretty good at estimating VO2 max values from distance covered over 12 minutes of running when you give a maximal effort. Now, the question is the level of error in the prediction, is that meaningful when it comes to cardiorespiratory's relationship or prediction with longevity and mortality? So let's think through an example here. So if I go out and do the Cooper test, the 12-minute run, roughly I would be able to probably cover a little over 2 miles. Now, I didn't go out and do this test, but I know from my most recent 5K performance, roughly where I would likely be when it comes to performing the 12-minute run test. So exrx.net has a calculator. If you're interested in it, you can plug in your distance run and it'll spit out a VO2 max estimate using the Cooper equation. And my estimate is 67 milliliters per kilogram per minute. Now, how does that compare to my real VO2 max value? I have had it tested in the lab in the last few months, and it's probably somewhere in the high 50s. So yeah, it's the Cooper test for me is overestimating VO2 max maybe by something like 8 to 10 milliliters per kilogram per minute. That would be roughly 2 to 3 METs or metabolic equivalents. So let's go back and look at that graph from the original study, the cardiorespiratory and longevity study that I showed you, and see if we change my estimate, my cardiorespiratory fitness estimate by 2.5 METs, 2 to 3 METs, what does that do to my supposed mortality risk? Now, in the graph on the x-axis, it only goes up to 15 METs, which is about 52 milliliters per kilogram per minute, which is below my VO2 max. But I just sort of use the top end of the graph as a high value. And then show if we go over roughly 2.5 METs lower, so let's say that's the level of error in this prediction, what is the impact on the estimated mortality risk? And what you can see by drawing sort of horizontal lines over to the vertical axis is that it really has pretty minimal impact on my risk estimation. It's not a dramatic change in terms of how far you're moving up that vertical axis. So for somebody like me who is, maybe wanting to do the Cooper test as a way to estimate my cardiorespiratory fitness compared to a lab test, it's not quite as accurate, but it gets me quite close. And relative to what we're trying to achieve here, which is health risk prediction, it doesn't really matter the level of error that we're seeing here in the Cooper test. Now, this is me as an example. What's the typical error for most people in the Cooper test? Going back and looking at that graph that plotted distance run versus VO2max, when I go and calculate the estimated VO2max values from distance covered and compare them to the directly measured values, most people in that study, that original study, are within 1 to 2 METs of their real value. When you look at their prediction, it's no greater than 1 to 2 METs off from what the real value is. So going back and looking again at this mortality graph and cardiorespiratory fitness graph, a 1 to 2 MET change in your estimate of cardiorespiratory fitness has really minimal impact on the overall mortality risk estimate. It doesn't change it a whole lot when you're looking at that small of a change in metabolic equivalence or cardiorespiratory fitness. Now, we see from the study from Cooper in 1968 that if you run maximally for 12 minutes, there's a strong correlation with VO2max measured in a laboratory setting. So what if somebody's unable or doesn't want to do a maximal 12-minute run or similar type of test? There's also a 1.5-mile version of the Cooper test. There are other approaches, and we'll go through a couple examples here. The first one is sort of a modified test where you do 1.5 miles, but instead of doing it maximally, you do it at a somewhat hard effort. So it's on a 13, rating of perceived exertion on the classic 6 to 20 RPE scale. If you're not familiar with that scale, that's fine. It just is sort of somewhat hard for the duration of the 1.5 miles. The person can run it, they can jog it, they can walk it. It's totally up to them, but it should be at a somewhat hard effort. So this particular study looked at this sort of modified 1.5-mile test, a sub-maximal test. And we can see by looking at the graph of predicted versus measured VO2max. So the measured VO2max in the lab, and then you used a sort of prediction here from a few different variables: sex, body mass, and time that it took to run the 1.5 miles or walk or jog the 1.5 miles. And we see that the estimate of VO2max is pretty tightly related to the actual real values. And the typical error here is roughly 1 MET. So 3 milliliters per kilogram per minute. That's around 1 metabolic equivalent. So in this example, the submaximal 1.5-mile running test or walking test or jogging test done at a somewhat hard intensity does a good job, again, of getting people reasonably close to the real value. And even in the worst case scenario, someone might be, a couple of METs or maybe 3 METs off of their real value. That still doesn't make a huge difference in the risk prediction when we think about cardiorespiratory fitness and its relationship with mortality. Again, you only really get big differences in the risk prediction when you go from really high fitness to low fitness. So the level of error that you're getting in this test isn't enough really to meaningfully change the interpretation. Now, one final example I'm going to give here is a pure walking test. It's called the UKK test or the 2-kilometer test. This is from the UKK Institute in Finland. That's kind of where the name comes from. And in this particular study, they actually did a smartphone-based version of this where they used the smartphone to measure heart rate. And then along with some other variables, they used in a prediction equation to estimate VO2max from this 2 kilometer walking test. And what you can see here is that, much like the other ones we've seen, this is a pretty good way of getting a reasonable estimate of VO2max, at least in this particular study. Might not work as well in every population, but it seemed to work pretty well in this group of individuals. All right, so what you could take away from the research we've covered in this video is that, yes, cardiorespiratory fitness is a strong predictor of longevity. Now, do you need to measure cardiorespiratory fitness or VO2max in a laboratory in order to evaluate health risk? No. In most cases, you can get a reasonably good estimate of your VO2max from a field test, like the 12-minute run, the 1.5 mile submax run, or a variety of walking tests, like the UKK test. The typical level of error in these tests is not going to meaningfully impact risk prediction when we think about the relationship between cardiorespiratory fitness and mortality and longevity. So all those people on YouTube, on social media, on podcasts saying that you need to go to a lab to have your VO2max measured because it's the most accurate way to do it. No, when we think about health determination, health evaluation, you really don't need to have a test done in a lab that's going to cost $100 to $200. And it's going to be a lot more complicated than one of these tests that you can use and then repeat on your own with little cost and with relative ease. So the last reason why you probably don't need to have your VO2max measured in a lab for determining health risk is the fact that most of these big studies that have looked at cardiorespiratory fitness, VO2max, and longevity and other health outcomes didn't actually directly measure VO2max itself. They usually have used work rate as a way to estimate VO2max or cardiorespiratory fitness. So the example study that we went through, in fact, used treadmill speed and grade to classify or estimate cardiorespiratory fitness. And that's the main way that it's been done in these big population studies that look at longevity and mortality, risk of death from things like cancer and cardiovascular disease, in part because it's just a lot easier to have people exercise on a bike or treadmill and estimate oxygen consumption from that without having to hook them up to a metabolic cart, because there's tens of thousands of people who go through these studies. So I think logistically, it would be complicated to actually do a VO2max test and directly measure oxygen consumption on that number of people. So that's further argument for why you really don't need a lab-based exercise test to measure VO2max directly in order to get a good sense of your overall health risk. It's about your ability to do work. The harder you're able to work during exercise, the lower your risk of early death and disease is going to be. Now, that doesn't mean that there's no value to doing VO2max testing in a laboratory setting. As we'll talk about in a later video, athletes may be a different story. There may be some value there in a lot of cases to actually getting assessment in a laboratory of an athlete's VO2max, along with some other physiological parameters that might be useful when it comes to tracking their training progression or predicting how well they may do in competition.